Welcome everyone to Princeton University's CITP seminar today with Professor Raluca Popa from UC Berkeley, who will be talking about a secure collaborative learning platform. Let's wait a few minutes for everybody to join in.
Hello everyone. Should I take over the screen though?
Let me introduce you a bit more. Yeah. So the seminar is being jointly sponsored by Princeton Center for Information Technology Policy, as well as the Center for Statistics and Machine Learning. Please note that this talk is being recorded, and the audience members have an opportunity to ask questions via the Q&A box. With that, it's my great pleasure to welcome and introduce Professor Raluca Popa. She's currently an assistant professor in the Department of Computer Science at the University of California, Berkeley. She has done really pioneering work in many aspects of computer security and privacy, particularly focusing on applied cryptography as well as system security. She is the recipient of multiple highly prestigious awards, including the Sloan Fellowship, the NSF Career Award, Technology Review's 35 under 35, as well as the Best Doctoral Dissertation Award from MIT. She's the co-founder and co-director of the RISE Lab at UC Berkeley, as well as the co-founder of a security startup called Prevail. So Raluca, it's a great pleasure to warmly welcome you virtually to this seminar, and we're really looking forward to your talk. Thanks.
Thank you very much. Thank you very much for the introduction, Pratik, and thank you for organizing, to you and to Jean as well. And I'm very, very happy to be here. I'm here in spirit, even though I couldn't be here physically. And so let me share my screen and start my presentation. Okay. Share. Okay, and let me know if you can hear. Otherwise, if you can hear or see the slides, or there's any obstruction to the screen, I'll assume there isn't, unless you let me know. All right. So one moment, I just want to make sure I shared new share. Okay, good. This is what I want. Great. Okay, perfect. Now it's perfect. All right. So yeah, I'm going to tell you about my recent work on a secure collaborative learning platform. So let me begin with the broader problem within which this fits. We oftentimes trust servers with our sensitive data, but we also often hear of server compromise. And some of these attackers steal hundreds of millions of data records, and that's because the servers are a central point of attack. And the reason why these attacks don't stop is that traditional security is fundamentally insufficient. It focuses on building taller and taller software walls around sensitive data to keep the attackers out. But software will always have bugs that attackers can exploit and get access to the data. Instead, my students and I take a different approach. We assume that attackers will break in eventually, and we want to be prepared even then. So instead, we are going to work on securing systems with the help of modern cryptography. So our work is providing to a client cryptographic guarantees of privacy and integrity, even if the server got compromised. And in particular, there isn't a central point of attack in that there isn't any one machine that you could go after and be able to steal all the data in the system. So to be able to implement this approach, one needs to design systems that, at all the different levels of systems that are used today. So for secure communication, secure storage, and secure computation. And my students and I have worked and contributed at every one of these levels. In secure communication, especially focused on end-to-end encryption for challenging settings, cryptographic storage, especially focused on preventing metadata leakage. So this is in addition to end-to-end encryption, as well as preventing equivocation from the storage server. And a lot of our work has been on secure computation, because you can imagine that it is much harder to compute when the data is encrypted. And here we've done work on securing databases, network processing, also general purpose programs. And today's talk is a direction in this secure computation work, and that is secure collaborative learning. So let me motivate the need for collaborative computation. A lot of organizations today wish to run cross-organization joint computation. However, oftentimes they have sensitive data that they cannot share. Here's an example in money laundering. So criminals, often launder money across different banks, and banks would like to detect the money laundering. But because the criminals hide their traces across different banks, it's hard to just look at any one bank's data and find them. That's why the banks want to learn from the aggregate data. It's actually so much simpler to see those patterns when you look at the data of all the different banks. But the banks can't share data with each other because they're in competition or because of privacy regulations and so forth. And in fact, so in the RISE Lab, we have a number of industry partners. And so we got to hear about a lot of use cases in this space. Even in the financial sector, there's more. Fraud detection or human trafficking is still primarily detected through financial forensics. And also for medical diagnosis and treatment, you can have much better studies if you can study across different organizations. For example, flu prediction, cancer diagnosis, but again, medical institutions can't share data with each other. And then there's all kinds of other use cases, even in the nuclear facility auditing or in cloud-based video analysis for home intrusion. So because of all these use cases that all pertain to the same problem of needing to collaborate without sharing data, my students and I have been developing the MC² platform for secure collaborative learning. And MC² stands for multiparty, collaboration, and competition. And it embodies the principle of sharing without showing the data. So you should be able to share data without showing it. This is a big open source project that I'm leading in the RISE Lab, so you can always go to this URL and try to use MC². So in the way we implement MC² technically is we actually have two different technical approaches because there's a fundamental trade-off between the two of them. The first one is secure multi-party computation or MPC, and the second one is hardware enclaves. So let me give you a brief overview of MPC because we are going to use it later in the talk. At a high level in MPC, you have end parties that have sensitive data they're not willing to share with each other. But MPC, interestingly, enables them to compute a function f over all their data, but without any party learning the data of another party in the process, other than the final result. So that sounds counterintuitive and it's very powerful, but essentially what happens is that the parties exchange encrypted data with each other, and they compute on the encrypted data while keeping it encrypted. And they obtain an encrypted result. For example, the best cancer treatment over all these hospitals or suspicious accounts for money laundering. And they only decrypt that result jointly and nothing else. Okay, so in the process, they didn't see anything about any other party's data other than the final result, which is very, very cool. So the reason I mentioned there's a trade-off between these two is that MPC becomes slow and expensive for complex computation and big data. And it also requires a compute cluster at each organization oftentimes. Hardware enclaves don't have these downsides, but they are specialized hardware that they require trusted hardware, which brings trust assumptions on the vendor, on the enclave, but also brings the required setup of you need those hardware enclaves to run on. And today it's actually better because there are cloud providers that offer hardware enclaves. But then they also suffer from side channels that the cryptography doesn't have, this issue. So this is why my students and I have been working on both of these directions, and we have contributed to both of them. Our contributions are aiming at reducing these downsides while keeping their benefits. So for example, in the MPC space, we have been developing efficient protocols for important workloads, such as neural network inference in Delphi, linear regression training in Helen, collaborative search in Dory, SQL analytics in Senet, and classical ML inference in our work by Bost et al. On the hardware enclave side, we've been focusing on reducing side channels. And in fact, our work eliminates an important class of side channels, namely the side channels based on memory access patterns leaking sensitive data. There's actually tens of those side channels that all go away when one designs protocols that are so-called oblivious. So the oblivious protocols are basically having the memory accesses be independent of sensitive data. So we've designed a number of such oblivious systems and efficient, because there's a challenge between obliviousness and efficiency there, such as Visor for ML inference, OCQ for distributed analytics, Oblix for multi-user search, Opaque for analytics within one cloud. And we also have contributed to general programs in CITP and Buster. So unfortunately, I obviously won't have the chance to tell you about all these works and how they work. This constitutes the MC² platform overall. But I still want to get some technical depth, and I want to go into one of these works, to show you a little bit of how they work. And I know that my student Wenting was here, so she told you about Helen and Opaque earlier this year. So I decided to instead focus on Delphi, so I don't bore you with the same thing. So I'm going to start talking about Delphi, which is one such work, but I wanted to see if before people have questions on the generic MC² platform or on the approach we take. So I'm happy to take some questions before going into Delphi. No, there's no questions. By the way, feel free to ask any questions. Don't be shy. I promise to be friendly. Okay. Well, I'll be asking you for questions. Yeah.
If I can ask a question.
Yeah, definitely.
There are some very interesting differences in the trust assumptions between the world of multi-party computation and the world of hardware enclaves.
Yeah.
I'm curious if you can talk about the trade-offs between those assumptions.
Yeah, definitely. So, also tied to those assumptions is the fact that different use cases need different ones of them. So in terms of purely assumptions, maybe let me go to the previous slide just because, to see all the trade-offs, not just assumptions. So in hardware enclaves, you definitely have to trust the vendor. Then you have to trust the enclave, and there's a lot of things to trust there, not just hardware. There's also, various types of low-level software to trust. Then you have to trust, when you trust the vendors, you have to trust their key management system and all of this. And people do have issues with, for example, trusting Intel. But, now there have been a number of different enclaves, including some academic open source enclaves, so that are trying to mitigate some of these issues, because, for example, the SGX enclave is closed source, so it's harder to trust it, if you don't see what's really running. Those are issues on the enclave side. Now, on the crypto side, it depends, again, the less you trust, in terms of a party's behavior, the more expensive the crypto is, the MPC is. For example, you could have maliciously secure MPC where you have n-1 out of n parties could be malicious. And we have done work like that in our Helen work, for example. And that's a very, in that case, you don't trust that much. You just trust yourself. You're the nth party, you trust yourself. And you don't have to trust so much about the behavior of the other parties. Now, of course, there's questions as to what data they put into the system, but that applies to both hardware enclaves and MPC. But then you could have MPC that's more efficient than the maliciously secure one, and you could have semi-honest MPC, which is faster. But then you have to trust that some parties are behaving correctly, you know, so that's an assumption. And there's all kinds of other questions where you say, okay, maybe we can't compute between our n parties because we're too slow. We're going to delegate to 2 parties, assume at least one of them is honest. So there's a whole spectrum of assumptions there. And of course, you also assume that the math is correct. But generally, you know, it's less that you trust any one entity in particular, the way you do, for example, with hardware enclaves. So I feel that people, at least are more comfortable trusting the math and this scenario in some cases than hardware enclaves. But as I mentioned, hardware enclaves have super advantages of performance.
Yeah, very interesting. I think we also have a couple of questions from the audience, one on the MPC side, one on the enclave side. I think on the enclave side, the question is, what is the reason why enclaves are necessary in the first place?
Yeah.
And side, the question is about the compute requirements at each organization. So for example, having a cluster at each bank might not be that prohibitive for banks.
Yeah, both are excellent questions. Thank you. So I see the first one is from Anya. So Anya, you're asking why are enclaves necessary? So sometimes, so I would say for at least 2 reasons. So sometimes the MPC is too slow. For example, if I want to, you know, to do extensive training data analytics, you know, in a strong threat model where, you know, the parties or the cloud could misbehave, then I can't really use MPC today. It's just too slow for that. Whereas enclaves are much faster. That's one reason. The second reason is if you want to run everything at one party. Let's say you want to run everything within one cloud. Well, in that case, MPC doesn't help you because MPC, importantly, can't just all run at one party. MPC has to run at different parties that have different pieces of a secret. Now, if there's only one party, then then all the secret can be put together and there's no security. So in that sense, in these 2 cases, I would say that hardware enclaves are actually necessary. And now I have another question from an anonymous attendee. Asking basically what Pratik said is the computation requirements for MPC, and imagine that banks could have clusters. So yes, banks used to traditionally have clusters. I feel like today, at least the banks we're working with, such as Scotiabank, Capital One, Royal Bank of Canada, a lot of these are actually on the cloud right now. And even if they do have their own cluster, they don't necessarily want to set up a new cluster for this collaborative learning. You know, if they're on the cloud already, they would love to just, upload some encrypted data there, and that cloud takes care of the, takes care of the computation, as opposed to having to set up a whole other cluster. So we are noticing in our, real use cases with the banks I mentioned that they do prefer to just upload encrypted data somewhere they can really trust, especially on a cloud they're already on. And, and then just go from there, as opposed to having to set up a whole other cluster that would take a very long time to get that to deploy. But great question. So people asking about how does Delphi scene and inference combine with explainable AI? It seems like obscuring the origin of the data would make it even harder to debug bad AI. Great, so we'll talk about Delphi in a moment, but in general, the direction of MPC and explainable AI. So I argue that if you have a training algorithm or inference algorithm that can provide explanations, then you can have those explanations also be computed with secure computation. It's true that the data will all be encrypted, and the only thing that you reveal is the final result, for example, a model that you learned or some prediction that you made, but you can additionally consider as part of the result the explanation. So if the machine learning or the AI can provide explanations, then those could be included in the final result released by the MPC. So in that sense, I argue that you can have both explainable AI and MPC. That's a great question, thank you. Great, thank you for the wonderful questions. So let's start, delving into some technical pieces here. We've talked high level so far, high level philosophy and approach. And in particular, today I'm going to tell you about Delphi. And Delphi is a system for cryptographic inference for neural networks. And this is joint work with my students Pratyush Mishra, Ryan Lekmo, Akshayaram Srinivasan, and Wencheng Zheng. So Delphi goes for a bit of a simpler setting than the n-party setting of money laundering, although I'll come back to that setting later. It looks at a two-party setting. So in this, you have a two-party collaboration, essentially. So the idea is that you have some applications where they have a proprietary neural network model, M. So a server is hosting a proprietary model, and that model is part of their business model, so they don't want to release it. It took a lot of money to produce it. Or it could leak about the training data, so they don't want to release it. On the other hand, you have a user with sensitive data that would like to get predictions from this model on their data, but they wouldn't want to share their data. So here's an example of a baby monitor. You have on the client side a baby monitor that's producing baby feeds and converting them to a feature vector X. And later, and the server has a proprietary model, and the server needs to produce somehow a prediction, whether the baby woke up or is crying or maybe is not breathing anymore. And so obviously this feed from the baby monitor is very sensitive, very, very private data. So there's a concern to send that to the cloud or to the server. And at the same time, the server has a proprietary model. So it's a concern to send that to the client. So how can we compute those predictions? Well, one possibility is to have the server send the model to the client. So the client on the edge uses its input and computes the prediction there. Unfortunately, that's not great because the client sees the server model, so a competitor can just get that model from a client, for example. Another approach is to have the client send the input to the server, so then the server can compute the prediction. But there's a ton of backlash against these situations because the server sees the client data. For example, there's been a lot of concern in the news about Amazon and Google listening to voice recordings. And there's been a lot of articles on attackers getting access to these baby cam feeds, as these baby cams are connected to the internet and streaming data. So none of these is great. We don't want any party to send their data to another party. So therefore, what we want is the client and the server to together compute the prediction M of X. Only the client needs to see, the server doesn't need to see the prediction result. But in the process, the server should not learn the private input X of the client, and the client should not learn the private model weights M of the server. Here we assume that the architecture is well known, but we don't want to reveal the weights of the model. Some things that we don't aim to solve in this particular work, although we have different approaches in the bigger MC² framework. But in particular in Delphi, we don't intend to prevent leakage that's coming from the prediction results. And there are attacks using simply the prediction result called prediction API attacks that can, over time, over multiple queries, figure out what the model weights are. And there's also defenses and mitigations to this, okay? But this is a complementary line of work, super important line of work, but it's complementary to Delphi, okay? In Delphi, we're concerned with obtaining this M of X without revealing M or X in the process of the computation. All right, so what has been done before? Well, let's take a look at two-party secure inference. And initially, they were based on something called the fully homomorphic encryption, FHE. I'm sure many of the security audience is familiar with it. And the problem with that is that it was slow. And also it was approximating significantly the neural network to the point that it had a significant accuracy loss. Later, people developed systems like SecureML, Gazelle, ZPC, Min9, and others based on two-party computation, in particular something called garbled circuits, which was great at retaining accuracy, but was still slow. And we'll see why one of these systems, Gazelle, is still quite slow. So in Delphi, what we tried to provide is both performance and accuracy in the two-party model. And I do want to mention there's some very, very interesting works in the three-party model. Pratik here has a very great work, Falcon, with his student Samir. And Samir is now a postdoc with me, so thank you, Pratik. And so Falcon is in a three-party honest majority model. But in that model, they're able to do not just inference, but training efficiently. And they're even able to protect against the malicious party. at the cost of needing another third non-colluding party. So that's a different model. It's also a very, very interesting model. And of course, there's trusted hardware work as well. All right, so what is Delphi? Delphi is two-party computation in the semi-honest setting. Namely, we are assuming that the client and the server are following the protocol. We are having actually a follow-up work right now that we're about to submit that protects even against malicious attackers. And it's based on Delphi. So in terms of functionality, we support arbitrary CNNs. And in terms of efficiency, we'll see that it's significantly smaller bandwidth, inference latency than prior work like GAZELLE. And we can also leverage the GPU despite it being encrypted computation. And we were also the first to run on realistic workloads in this setting, namely CIFAR 100 and ResNet 32. All right. So a brief reminder on what convolutional neural networks are for people who are not familiar with them, because we're going to use this structure. All you need to know for this talk is that they are an alternation of convolution and then non-linear layers. So basically linear, non-linear, linear, non-linear, linear, and so forth, all the way until from the input till the prediction. So the non-linear layers have, for example, use a function like Ralu, which is a non-linear function. Okay, so let's start with the prior state of the art to Delphi, which is GAZELLE. And let's understand why GAZELLE was too slow so that we can then figure out how to improve it. So in GAZELLE, the insight was to develop specialized crypto for each layer because that enables efficiency. So here's how GAZELLE works. For linear layer, what they do is the client sends the encrypted input of the client to the server, encrypted with some linearly homomorphic encryption scheme. What this encryption scheme is it has the property that if you add up two ciphertexts in a special field, but then you get the encryption of the sum of the underlying values. So it's a very convenient property that the server then uses to obtain the encryption of the model times X. So the server needs to compute the model times X, but then it also adds a random S to this for later masking, okay? And can compute this encryption C using the homomorphic properties of the encryption. So far it's pretty simple. It's gonna send this C to the client. And the client is going to decrypt it and is going to obtain Y, which is just gonna be the model times X, which is what you want to compute, but plus the secret S, because things are supposed to still be encrypted until the very end. Now you have the non-linear layer, which is the Ralu activation. And that's really hard to compute using encryption because it's non-linear. So they're using garbled circuits, which is, garbled circuit is a two-party computation tool that is particularly good for bitwise operations like Ralu. So we're just going to use it. You don't have to understand how it works. We're just going to use it as a black box here. But the point is that it can take inputs from two parties and output, it can take and output a function over the two of them, okay? But we'll want to use it rarely because it's actually quite expensive. So the client is going to input Y, which was mx plus s, and the server is going to input s. So they're going to compute the difference, which is going to be mx. Mx is what the linear layer was supposed to output if this was plain text computation. And then, but we can't release, then we have to apply Ralu inside the garbled circuit. And then we'd like the output of Ralu, but again, we can't release it. We have to release it encrypted because we have more iterations to go and we can't show the final, any plain text data, any intermediate result until the very end. Okay, so we release it from the garbled circuit encrypted. So this is going to be, used in the next phase. Okay, in the next repetition, so you repeat layers and layers like this. Okay, so this is GAZELLE. So Okay, so how do we design Delphi that's more efficient than Gazelle? And one thing I find interesting about Delphi, I find many things interesting, of course, but one thing I really like is this synergy of cryptographic systems and machine learning design together. So we contribute techniques at the intersection of these three. So first, let's start with systems. And in old-fashioned systems way, you first try to understand what are the bottlenecks of the existing work, and then you try to address them. So let's understand what the bottlenecks are with Gazelle. What's expensive with Gazelle? Well, first, this encryption is big and takes bandwidth because it's linearly homomorphic encryption. Second, this, and then again, here X is a big vector or a matrix. Okay, so it's pretty big. Then to compute this linear function, you have to use homomorphic operations that are not able to leverage the GPUs, so you lose that extra speed up that the GPU could have given you, that people normally use in this situation. And then the garbled circuit I mentioned is pretty heavy tool, and that adds significant bandwidth and computation as well. So overall, what you have with Gazelle at this moment, for SNet32, for inference, you send over the network 600 megabytes. That's a lot for one inference. And then also the communication is 82 seconds latency. So that's not great, because if your baby stops breathing, you need to know right away. Or if they're waking up, you need to know right away. You can't wait that long. Okay, so let's try to fix these bits of Gazelle and try to remove these bottlenecks. And that's where a lot of the cryptographic techniques come into play. So let's try to first improve this top part of the protocol. Well, wouldn't it be nice if instead of encryption of X, we were to send X plus a randomness? And then it would be great to just do linear operations as if it was on plain text at the server, because then we could even use a GPU. That would be great. So how to achieve that? So the idea is the following, is that we could actually do the encrypted computation, the expensive one, in a pre-processing phase before the baby moved, before there's any online input. And we can do that on randomness, but then use that randomness to send in the online phase exactly this X plus R. So when the baby does move, we can efficiently compute this part of the protocol. Okay, so again, we're going to use exactly as in Gazelle in the offline pre-processing phase and run that on randomness, and then use that randomness in the online phase to do the actual X plus R. So here it is how it actually works. Let's see it concretely. So in the preprocessing phase, we're going to sample a value R, and we're going to send encryption of R. The server is going to sample randomness S, and it's going to compute the same thing as before, but using R, the encryption of R, as opposed to the actual input X, and then sends it to the client. The client decrypts and has MR plus S, and they're ready for an input in this way. Now later, let's say that the sensor in the baby's room detects a movement and produces an input, or detects something is wrong and produces an input. And then the client sends the input X plus R. So simply like this added, but within modular field. And then the server only needs to compute M times this X plus R plus S, which is a linear operation that is fast, and you can actually use GPU with it. Sorry about this, going back here. Okay, you can actually use GPU. And then we're going to also still use the garbled circuit so far, and we're going to input Y to it and some extra randomness for masking, and then Z, and similarly things are going to happen in the GC that output Ralu of plus the randomness R2. So the nice things of this protocol are that we're sending X plus R in the online phase, and we're also, can run this using a GPU. Okay, so it's much, much more efficient. So in the online phase, we can answer to a query in 13 seconds, which is faster than 82 seconds from the moment there's input from the user. Now, the communication is still, it's almost half, but it's still pretty large, and that's because of the garbled circuit. Okay, so the next step is to try to, remove as much as possible the overhead of the garbled circuit. Okay, so here is, let's look at what prior work did. So people have struggled a lot with ReLU in general in MPC because it's non-linear. So what prior work like CryptoNet, SecureML do is they replace the ReLU with an approximation, like quadratic activations, like a quadratic polynomial. And they show that in some cases, for some simple networks, it actually performs well in terms of accuracy. But on other networks, like the more realistic networks we're considering, ResNet32, the accuracy is very poor. And at the same time, these quadratic activations are very fast in 2PC, so they'd be nice. So sometimes they work, sometimes they don't work, right? And so the intuition we had is, great, how about we leverage them when they work and don't use them when they don't work? So at least we get the speed up from when they work. Right, so the idea is to combine quadratic activations and ReLU. But the hard part here is that you don't know which layers is okay to approximate with the quadratic activation and which layers is not okay and you have to keep ReLU. You don't know. We tried every other one and you get bad accuracy. We tried all kinds of things and there doesn't seem, these things are not well understood how, these neural networks anyway. So it's not clear. We couldn't find any rule. There isn't really a rule that we're aware of as to when to use quadratic versus ReLU. But it's important that we know when it's used for certain layers actually gives great performance and when it's for others, it doesn't in terms of accuracy. So here's where we employ techniques from machine learning. So it turns out that there's this really cool thing in machine learning called the neural architectural search. So this tool was used in other contexts and we adapted it to optimize the neural network for MPC efficiency and accuracy. The idea is that it can search through a space of different possible architectures, different combinations of ReLU and quadratic, and produce some that are, at least a certain accuracy threshold. So by adapting this technique from machine learning, we develop a planner in Delphi that takes as input an accuracy threshold T and takes as input a CNN that's all ReLUs, and then runs this neural architectural search which tries inside its belly all kinds of combinations of ReLU and the quadratic, retrains on the data, and finds a network that is hybrid, but has at least that accuracy T, okay? And tries to find a network that has, the most quadratic activations one can, but still have that accuracy threshold T. And, to make this work, we actually had to do a lot of different things to adapt it to this setting, and the paper describes them. I won't go into the details of that. But let me go over the end-to-end workflow of Delphi, and then I'll take some questions to see if people have understood the design so far. So here is how we put all of what I said together. So basically, the server initially trains an all ReLU network on whatever training data the server has and produces an all ReLU CNN. Now it's going to run the Delphi planner using a certain accuracy threshold. For example, it says accuracy should be at least 70%. And it feeds that into the planner alongside with the all ReLU CNN. And our planner outputs a hybrid CNN, which has ReLUs and activation, so it's more efficient at doing 2PC. Then in the pre-processing phase, the client and the server are preparing the randomness, as we saw, ready for when the client has an input in the online phase. In the online phase, the client has an input X, and they're running our online phase, which is going to be quite fast. Fast also because of the optimizations I mentioned, and fast because a bunch of layers will now be quadratic, and that is much faster than garble circuits. So I'm going to, present the evaluation and show you in the, the actual concrete numbers that Delphi is improving. But first, I wanted to see if people have questions on this technical design of Delphi. Any questions on it? Is it clear? Didn't tell you all the details, of course, but I wanted to give you a high-level sense of how the work.
Maybe while the audience members are thinking about their questions, I can begin with one. Could you give us a sense of the accuracy loss if all of the ReLU activations were replaced with quadratic activations?
All the ReLUs are replaced with quadratic. So it depends a lot on the network. If it's, for example, ResNet 32, and depends on the data, if it's CIFAR 100, then it's horrible. Basically, it doesn't converge. Okay, so it basically doesn't converge, because we even tried that, and it doesn't converge. But now, if you have an MNIST data set and a shallow network, it works well, very well. It's a small accuracy loss of, I would say it's at most 10% accuracy loss, and some works have shown even less. So that's why it varies wildly, and that's why it's important to use something, like neural architecture search that is trying to make sure the accuracy stays above a certain threshold.
Okay,
yeah.
We have another question from Peter Ramage about quadratic activation still being nonlinear. So where does the improvement in performance come from in terms of replacing quadratic activations with ReLU activations?
Yeah, great question, Peter. So while quadratic activations are not linear, MPC is still very good at doing them. They're merely a second degree polynomial, so we can still use, efficient techniques. There's some, depending, for cryptographers, secret sharing based and, homomorphic, somewhat homomorphic based. There's various techniques one can use for quadratic activation. So there are known protocols and they're very, very fast, because they're not that super different from linear, whereas ReLU is just so not polynomially looking. Yeah. Thank you for the question. Any other question? Okay, great. Danny has a question. A follow-up for replacing ReLU in network compression, quantization hurts accuracy, and it's common to retrain a network to gain back accuracy. Have you tried replacing a trained network's ReLU and refine it? Yes, absolutely. So the way neural architecture works is that it's essentially retraining the network when you replace layers. It's retraining the network and it's trying to see what accuracy you're obtaining right now. Yeah, the neural search seems like an auto ML approach. Peter is asking, kind of in spirit, yes, I would say so. And now an anonymous attendee is asking a minor systems question. The preprocessing is a handshake that has to happen at what point? Once in the lifetime of MC square system, or is the regular client event? Very good question, thank you. The preprocessing has to happen, so you do it in the background, and you do need to preprocess something for every client input. So in the case of Delphi, you need to be prepared with randomness for every client input. So for every client input, you have to generate the corresponding randomness. So basically, we're going to preprocess a bunch of randomness, as many as you can store around, and then wait for client input. That client is going to use some of them, then it can generate more and more randomness. So I would say it's a continuous process. Thank you. Thank you for the questions. Okay. So let's talk about evaluation. So I mentioned Delphi is an open source project, so feel free to go and play with it. It's on the MC Squared project website, where we have a lot of our MC Squared open source. And we evaluated it on ResNet 32 network on CIFAR 100 dataset. And the question is, we tried to answer multiple questions. Here are two of them. does Delphi's planner preserve accuracy, right? With all the quadratic activations, it's a question we really need to investigate. And second is, does Delphi's protocol reduce latency and bandwidth, right? So does it actually help all these techniques? So here's a graph showing you accuracy on the y-axis and then the number of non-ReLU layers. So basically I'm increasing the number of non-ReLU layers. The red line on the top is the all ReLU baseline. It has an accuracy of 68%. That's the best one. Now you can look at the green line, and what the green line shows is that I'm actually going to replace some ReLUs with identity, not with quadratic, with identity. Identity basically means you remove those layers, okay, because it does nothing. So you can see that the accuracy goes down, very down. But if you look at the blue line is you replace ReLU with quadratic, okay, and the accuracy doesn't go down so much. So this shows a bunch of things. This shows that quadratic is actually performing better than just removing a layer with identity. So it's still helping in training. And in this particular case, with 25 quadratic layers, so you remove 25 layers instead of being ReLU, they are going to be quadratic, you get only a 2% accuracy loss. And again, these layers are carefully chosen by the planner. These are not any 25 layers, okay? So you get a small loss in accuracy, but those 25 layers with quadratic are gonna be way faster than with ReLU, which is going to also show up in this graph. So here we're gonna see the latency to do an inference as depending on the number of non-ReLU layers. So Gazelle, the prior work, stays around 80 seconds, right? Because they have all ReLU. In our case, Delphi, you can see how the inference time increases significantly, from under 20 and goes really down as you make more and more layers be quadratic. So it gets almost 20x performance improvement over Gazelle. And similarly with bandwidth, so this graph shows you the data transferred in gigabytes on the y-axis. And on the x-axis is we increased again the number of quadratic layers. And as you can see, the quadratic layers are really helping drive down the bandwidth, because I mentioned quadratic layers are so much more efficient than garbled circuits, in both in communication and in performance, in compute time. So, overall, Delphi achieves, significantly faster and efficient inference as compared to the state of the art. And it does so by combining techniques from systems, cryptography, and ML. Our full paper version is, on ePrint. And as I mentioned, it's open source. And so I'm going to go back to, wrap up on the MC² side of things. Delphi is just, remember, a piece of MC². But I just want to see if there's any questions about Delphi overall, about the evaluation, or about, the system before I go on. Okay, no questions, that's fine. I'm going to take more questions at the end. It's great. Okay, so now let's, so we saw Delphi, which is one piece of the bigger MC² ecosystem. So kind of let's zoom back and talk about MC² overall. So I mentioned all of, not all, but most of our projects in MC² are open source at this link. And we're happy that we already had some adoption. So IBM Research is using the analytics component, Opaque, of MC² for 2 medical use cases. Ericsson is using MC² to train decision trees for telecom data. And Financial is using MC² for credit scoring. And the anti-money laundering use case I mentioned at the beginning, we're working on that for 1.5 years right now with Microsoft and Scotiabank. We've completed 2 POCs successfully, and also, been working with regulators. It's obviously a huge, huge use case because, to be able to handle bank data over different banks, that is definitely a regulated activity. And so right now we're in the process of doing a cross-bank POC with the Royal Bank of Canada as well. So this is a very ambitious use case that's likely going to take still a bit more to come through, especially considering the regulation. But it's very, very, very exciting because not only is going to help find money laundering much, much more efficiently, but can also be used to detect human trafficking, sex trafficking, because financial forensics still remain a primary way to detect those. So we're very, very excited about this use case as well. All right, so you've seen, an overview of our work so far. So where are we headed? Well, there's all these other use cases I mentioned that, our RISE Lab industry collaborators are having, and they need to use, something like MC² for. And we just don't have the bandwidth to manually, help them out to deploy each one of them and maybe have a custom MPC like Delphi for each one of them. That's just too much to do, for each one of them. That's why we are, transforming MC² into a efficient, secure collaborative computation for everyone. Okay, so we want anyone, so for everyone part, we want anyone to be able to use MC² without being crypto experts. So for that, in our recent work, Cerebro, we developed a Python DSL. So any non-expert can write their collaborative task in Python with no understanding of the underlying crypto. And this, it's not just to express computation, but also to express end-to-end policies. For example, when is it okay to release a model in terms of privacy, right? Maybe you need to add, privacy policies like differential privacy, or maybe you want to check that the model is accurate enough for every single party is going to benefit, not just one party. So you can implement all these kind of end-to-end policies to check a model before release or to do auditing and things like this, in addition to computation. And this, again, can be implemented by, someone can express something like this with only Python knowledge, so they don't have to be experts. Then, once we have the task expressed by them, by the non-experts, the question is how to run it securely. So we've already contributed tools for efficiently running certain workloads, and other people have also contributed many other existing amazing building blocks that we would also like to leverage. But the question is, how to automatically compile that program expressed in Python into the most efficient combination of different MPC tools, ideally reproduce Delphi automatically. So we've been working a bunch on this direction, and the first thing we contributed is in our recent work, Costco, is cost modeling. So before you can figure out how to combine different works, you need to cost model them. And Costco can automatically cost model MPC protocols without manual work. And then the next thing we're working on is an optimizer that now we have cost models for all sorts of MPC tools. What's the most efficient way to combine them for a task, and how to do that efficiently? And we've done a bunch of work on this. There's also other people in the literature that try to figure out how to do these combinations, but there's still a bunch that needs to be done in this space. One step forward is we believe that this cost modeling that's automatic can really help this agenda. So this is a very, very exciting agenda. And if any one of you wants to work on and, come up with ideas, I think it's super, super exciting. Ideally we can start generating all this, automatically all these protocols that, get accepted to Oakland and things like this. That would be really exciting. And then we could have all these many use cases use, MPC without a lot of manual work. Great. So before I conclude, I just want to mention that this work is thanks to my wonderful students. And this is a COVID-19 group photo. Unfortunately, this is how they look today. And we also tried the equivalent of a fun photo, but that came out pretty strange. If you look on the left side at Yun Song, I'm not sure what Zoom did to him. But yeah, thanks to my wonderful students. And I'm happy to, take questions about our secure collaborative computation framework. Thank you.
We have a few minutes for questions, and maybe I can begin with one. So Raluca, you showed using the Delphi protocol how latency and throughput costs of secure inference could be reduced by an order of magnitude. I'm thinking about applications in which a server might have to serve many clients concurrently, in which case even latency of the order of a few seconds could be quite prohibitive. So I'm wondering, where do you think the next order of magnitude improvements will come from?
Yeah, good question. So one thing about, and actually this is something I'm working with your wonderful student, Samir, is so he's had this idea of always wanting to investigate the GPU farther for secure computation. And one thing that we observed during Delphi, when we did Delphi, is we observed that you could batch, if you could batch multiple clients, you have all these concurrent requests, right? You shouldn't do them one at a time, because then you spend all that time. Maybe you could batch multiple of them. Maybe you wait a few milliseconds for each to align them or something, and then you batch multiple of them. And what you do then is you can use the GPU to compute batched inference, to a large extent. At least the linear part can be batched. So that's one thing we're trying to investigate that ideally should improve throughput significantly. Besides that, where do I think improvements will come? I would say always we tend to come up with better crypto. It seems that every few years there's a significant improvement in performance. That's one place. Another place is, I think, looking more at systems aspects of MPC. I think that people who worked on MPC, they've done so great in all those new techniques and implementations, but they haven't looked a ton of the system side. So for example, even page handling, right? MPC runs out of memory really fast. As soon as you hit secondary storage, you're basically it freezes. So better page handling for that, better memory management for that. I would say even better, distributed protocols for that, because crypto is a monolithic computation, and how do you distribute it? So I would say systems people working and thinking about how to improve MPC would also bring significant performance improvements.
Oh, very cool. I think speaking of systems people, we have a question here from Mike.
Yeah, Mike. Hello, Mike.
Mike is asking, do you think there are general lessons here for broader applicability? With a lot of this type of MPC, they're either very general approaches, which tend to be slow, or very customized algorithms, which tend to have moderate performance. In this case, any general CNN is obviously pretty important, but are there also broader learnings applications here?
Yeah, no, this is really a great question. I think there's a few of them. So one of them is try to identify what are units of computation that show up a lot. So one of them is matrix multiplication, right? It shows up in so many learning algorithms. If you can speed that up, for example, if you can have a GPU performant, secret sharing based, matrix multiplication, and a lot of different protocols could use it. Another one, for example, is the Raluca. So I would say one philosophy here is to understand what are the units of computation that are super commonly used across the board, and make those very fast. And then people can reuse those in many different applications. So I would say this is one learning lesson. Another lesson is to do more, to do planning. So not just design the crypto, but do planning, system level planning or machine learning planning. For example, in a lot of our work on SQL or even this machine learning work, is you realize that crypto changes the rules a lot. So you need to come up with systems techniques, to rethink of how your planner would work in terms of the new cost models and the new model of computation. So I would say, yeah, leveraging techniques from systems for the crypto, that would also be a great lesson. Yeah, I would say these two patterns, could bring us a lot of continued performance improvements.
All right, I think with that, we are out of time here. So I'd like to conclude by thanking Professor Raluca da Popa again for this wonderful and very, very exciting talk, and to all of the attendees for being here. Goodbye.
And thank you, everyone. It was really great how engaged you were. I really enjoyed it. And even though I wasn't there physically, I hope to be there soon, but I was there in spirit. So thank you. Bye.